It's a colossal construction site that's literally changing the face of Europe. A project designed to make life easier for millions of citizens, to smooth the flow of goods, and even to reduce carbon emissions. But how do you pull off such an incredible feat? By creating a corridor that connects Scandinavia to the Mediterranean seamlessly, along a route stretching over 5,000 kilometers. If the project sounds crystal clear on paper, it's a whole different story on the ground. To bring this insane vision to life, extraordinary works are underway. For example, under the Alps, where they're digging the largest railway tunnel in the world, or under the Baltic Sea, where they're building the longest immersed tunnel on the planet. From north to south, east to west, in this new video we're going on a tour across Europe's multi-billion euro construction sites that will permanently reshape the map of the continent. Welcome everyone to this new episode of Looking For. But before I show you what these new projects will look like, let me introduce you to Merlin AI, an all-in-one AI tool. They're giving our audience an exclusive 75% discount, and we'll show you exactly how to claim it at the end. For videos like this, our research is scattered. Articles, PDFs, notes, multiple AI tools, and since each tool is good at something, subscribing to all of them gets expensive. Merlin puts all top LLM from ChatGPT, Claude, Gemini, and more under one subscription, so you pick the best model for each task without paying for each separately. The project's feature works as a personal research hub. Drop in your links, PDFs, and notes, then ask questions across all of it at once. Need something deeper? Turn on Deep Research and get a structured report pulled from multiple sources. There's also image and video generation, all without switching tabs. On price, ChatGPT, Claude, and Gemini are each around $20 a month, and that adds up fast. Merlin is cheaper because they buy API access in bulk, and most people never use $20 worth of credits anyway. To get the deal, hit the pricing page, go to Stripe checkout, apply the promo code to the annual plan, and it will drop to $60 for the year, about $5 a month. This link is in the description and pinned comment. We don't know how long it lasts, so grab it while you can. Now, back to the first tunnel of our video. The first, starting from the north, is set to become nothing less than the longest immersed road and rail tunnel in the world when it opens in 2029. Connecting Denmark and Germany, the Fehmarn Tunnel will save massive amounts of time and revolutionize logistics. Today, to get from the Danish port of Rødby to Puttgarden on Germany's Fehmarn Peninsula, there are two options. Either take the ferry, a 45-minute crossing with fixed schedules and limited capacity, or drive around by land, a detour of nearly 160 kilometers. And this route between Copenhagen and Hamburg is one of the busiest. In peak summer, lines can get ridiculously long, nearly 3 million passengers between June and August 2025, with peaks of 150,000 passengers over just 3 days, according to the ferry operator. And that's not even counting freight. It's gotten so bad that some people actually fly between Copenhagen and Hamburg just to save time. To fix this overloaded system, Germany and Denmark agreed to build the tunnel in 2008 after long negotiations. When it opens, Denmark will be just 10 minutes away by car from Germany, and only 7 minutes by train. With this tunnel, trains will finally become a real alternative to flying, while also providing a much faster rail and road connection for freight between Scandinavia and Central Europe. Unlike the Channel Tunnel, the Fehmarn Tunnel isn't bored through the ground, it's immersed. It lies directly under the seabed, 40 meters deep. 89 watertight sections, each 200 meters long, will be towed, submerged into a trench, then assembled and placed 40 meters below the sea. Designing an immersed tunnel like this is a delicate operation because it has to meet very specific constraints. For example, the tunnel sections must be light enough to float during transport, but heavy enough to stay on the seabed once submerged. They'll rest on a gravel bed that acts as the foundation, installed by a remotely operated robot. To make that perfect bed, an 18-kilometer-long trench has been dug in the Baltic seabed. About 15 million cubic meters of sediment have been excavated. On land, teams are building the 89 giant tunnel sections at a dedicated factory on the Danish coast. Each standard section is 217 meters long, 42 meters wide, and 9 meters high. Each one weighs more than 73,000 tons, 10 times the weight of the Eiffel Tower's metal frame. Absolute monsters of reinforced concrete. The factory itself is just as impressive. The construction site covers over 500 hectares. Inside, 6 automated production lines are building the watertight tunnel sections. Robots weld 1,500 tons of steel every week to music. In total, the factory will use 360,000 tons of steel and 3.2 million cubic tons of concrete. By February 2025, 9 of the 89 sections were completed, 7 standard and 2 special ones, about 10% of the tunnel. The first element was poured in May 2024 and inaugurated on June 17, 2024 by King Frederik X of Denmark. That ceremony marks the start of the immersion phase of this €7 billion project. Denmark is covering most of the cost. A colossal worksite employing more than 3,500 workers from 40 different countries. Once lowered and connected with watertight joints, the sections will form a continuous trench, which will then be covered with sediment and rocks to protect it from marine currents and ship anchors. In total, the tunnel will have 4 separate tubes, 2 single-track rail tubes and 2 double-lane road tubes. But the project also raises a lot of concerns, especially environmental ones. The Baltic Sea is home to protected species like the harbour porpoise, which is endangered in these waters. To avoid disturbing them, acoustic monitoring systems have been installed to pause construction whenever porpoises are nearby. Sound deterrent devices are also used to keep them away. Artificial reefs will be created as well, to give new shelter to marine life that loses part of its habitat along the tunnel's path. Another unusual feature of the site, it's literally mined in the most literal sense. The Baltic Sea is full of unexploded bombs and mines left over from World War II. Around 1.6 million tons of old munitions lie on the seabed of the North Sea and the German Baltic. Before digging the trench, bomb disposal teams had to inspect every square meter of the seabed. Unexploded ordnance, including 125-kilogram depth charges, was found in both Danish and German parts of the Fehmarn Belt and has been safely removed and neutralized. A dangerous and meticulous job. Explosive. That's also the word to describe the second massive project on this corridor. The Brenner Tunnel. A strategic passage between Austria and Italy, and one of the few ways to cross the Alps. At 1,370 meters above sea level, the Brenner Pass is the lowest and busiest crossing between the north and south sides of the Alpine Ridge. Every day, more than 2,200 trucks pass through. That constant flow creates noise, pollution, and traffic jams that choke the Alpine valleys. Residents of Italy's Isarco Valley and Austria's Tyrol region have been suffering from it for decades. So, Austria and Italy came up with a radical solution. Go under the mountain instead of over it. Once completed, the Brenner Tunnel will be the longest railway tunnel in the world, 64 kilometers long. It'll surpass Switzerland's Gotthard Tunnel, which measures 57 kilometers and currently holds the record. And, by the way, if you're curious about the engineering secrets behind that project, I'll leave a link to my video about it in the description. The Brenner Tunnel will connect Fortezza in Italy to Innsbruck in Austria via a railway line dug under the Alps, reaching depths of up to 1,720 meters beneath the mountain. Passenger trains will travel at 250 kilometers an hour and freight trains at 120 kilometers an hour. A huge contrast with the old historic line, over 150 years old, that winds through steep mountain slopes where freight trains struggle to climb. This isn't a new project. Construction began back in 2011, but it's now entering a decisive phase. In September 2025, teams achieved the final breakthrough of the exploratory tunnel, connecting the Italian and Austrian sides for the first time. The The works are divided into 4 lots, 2 of which are already complete. The tunnel is scheduled to open in 2032. Originally, it was supposed to be ready for 2025. Once operational, the trip between Fortezza and Innsbruck will go from 80 minutes to just 25. A major time saver, made possible by the efforts of thousands of workers toiling every day in extreme conditions. Digging more than 1,000 meters under the Alps is a Herculean task. To move forward, they use tunnel boring machines over 100 meters long and weighing around 2,700 tons. These giants chew through rock a few meters at a time, grinding it down with steel teeth. Depending on conditions, they advance between 10 and 27 meters per day. But under certain parts of the mountain, especially beneath rivers, things get tricky. The rock there is soaked with water, and using a TBM would risk a collapse, so they have to freeze the ground. The principle? Inject liquid nitrogen into the rock to freeze it. At minus 196 degrees C, it freezes the ground effectively down to minus 35 degrees C. Once the ground is frozen, the area becomes stable, allowing the tunnel boring machines to continue safely. This method, called ground freezing, has been used on other major projects, but never on this scale. Workers operate in extreme conditions, a surreal world of ice and stone deep inside the Alps. The ventilation system is another huge technical challenge. Over 64 kilometers, trains travel at high speed, generating both heat and air pressure. Parallel ventilation tunnels have been built to refresh the air and remove the heat. In case of fire, these same tunnels serve as emergency exits, a vital dual function. Every 333 meters, an emergency passage links the 2 main tubes. To remove the millions of tons of excavated rock, the site uses a gigantic conveyor system stretching over 66 kilometers. These conveyors carry 5,000 tons of rock per hour. Colossal. Without them, 190 trucks per hour would have to drive through alpine roads. A mountain giving birth to a mouse? Not at all. According to estimates, the tunnel will be a powerful economic driver for this part of Europe. The number of trains will double compared to existing lines, and they'll travel much faster. Even more important, the Brenner will help shift a large share of freight transport from road to rail. Currently, 2.5 million trucks cross the pass every year. The goal is to flip the ratio, from 70% road and 30% rail to 30% road and 70% rail. Then there's the ecological impact. While trains are clearly greener than cars or planes, building such a tunnel still raises questions. It's expected to generate around 2.8 million tons of CO2 equivalent. But according to a 2024 study by Eurat Research, the tunnel could offset those emissions in 5 to 18 years, depending on how much freight shifts from road to rail. And finally, a key piece of information, the cost. Originally estimated at just over 6 billion euros, it's now between 8 and 10 billion euros. Half of it is funded by the European Union, the other half split between Italy and Austria. Norway is building the most extreme road tunnel ever. It's a true engineering feat designed to overcome geographic constraints and bring people closer together. An unprecedented construction project packed with record-breaking achievements. In southern Norway, beneath the breathtaking fjords that have made the region and the country famous, a titanic construction site has been underway since 2018. Called Rogfast, this project hides a monumental achievement. At 27 kilometers long, it's set to become the longest underwater road tunnel in the world when it opens in 2033. More importantly, it will also be the deepest road tunnel ever built, with certain sections plunging nearly 400 meters below sea level. A multi-billion euro megastructure that already raises many questions, particularly about its feasibility, as water infiltration has already been detected on site. Fasten your seatbelts and hop into our amphibious car, because today, Looking 4 is taking you underwater, deep inside Norway's Rogfast Tunnel. Welcome everyone to this new episode. To truly understand the scale of what Norway is undertaking right now, we first need to set the geographic context. Known for the beauty of its landscapes, Norway is a rugged country that delights tourists who come to admire its natural wonders. And the country's appeal keeps growing year after year. But for residents, often faced with real journeys just to travel between cities, reality can be quite different. A reality that is even more pronounced along the coast, far from Oslo, the capital located in the east. Today, driving between Bergen, the country's second largest city, and Stavanger, Norway's fourth largest, takes nearly 5 hours. That's roughly the same travel time as driving between Paris and Lyon in France. The difference? The French route covers more than 450 kilometers, while the Norwegian journey is only 208 kilometers long. This gap is explained by geography. Between Bergen and Stavanger, drivers currently have no choice but to take ferries, which significantly slows down the trip. To improve connectivity between cities, modernize national infrastructure, boost local commerce, and encourage tourism, the Norwegian government launched a massive project, the modernization of the E39 coastal highway. Stretching 1,360 kilometers, it's considered one of the most scenic roads in the world. It runs from Trondheim in the north to Kristiansand in the south and eventually reaches Aalborg in Denmark. Today, it takes 21 hours to travel the Norwegian portion alone, which includes 7 ferry crossings. The goal is to eliminate these crossings by building tunnels and bridges, effectively cutting travel time in half. A simple idea on paper, but far more complex in reality. Proof of that, the project isn't expected to be completed before 2050, with a total budget exceeding $40 billion. Among all these major innovations stands one flagship project, undoubtedly the most ambitious and technically demanding of them all, the Rogaland Fixed Link, also known as Rogfast, literally meaning the fixed link of Rogland. This tunnel will connect Randaberg, just north of Stavanger, to Bokken, a strategic point along the Stavanger-Bergen route that currently requires a ferry crossing over the Boknafjord and Kvitsøyafjord. Built under the authority of the Norwegian Public Roads Administration, the tunnel will pass beneath the island of Kvitsøy, home to the town of the same name. A dedicated exit will allow access to Kvitsøy, which happens to be Norway's smallest municipality. The tunnel is expected to significantly improve connectivity along Norway's west coast by creating a faster and more reliable link between the Stavanger and Haugesund regions, promises Ann-Britt Moen, one of the project managers at Skanska, the company responsible for building the northern and deepest section of the tunnel. According to her, Rogfast could save drivers around 40 minutes between the two cities. Most importantly, it will put an end to ferry lines, waiting queues, limited schedules. While the drive may offer fewer scenic views, it will be open 24/7, year-round. Freight transport logistics will also become far more efficient. But this time savings comes at a price. Rogfast will measure 26.7 kilometers in total. While it doesn't rival rail tunnel records, it will become the longest road tunnel in the world, surpassing another Norwegian tunnel, the Lærdal Tunnel, which stretches 24.5 kilometers and opened in 2000 after 5 years of construction and decades of political debate. The Lærdal Tunnel cuts through a mountainous region beneath 2 fjords and is a masterpiece of engineering, featuring 18 turning bays that allow drivers to turn around if necessary. It's even become a tourist attraction in its own right, thanks to its lighting system. An artificial northern lights installation illuminates its 3 main turning caverns, adding a touch of magic to the journey. And Norway isn't alone. Across Europe, massive infrastructure projects are multiplying to improve mobility, even if that means literally moving mountains. I've linked a video in the description about 2 ongoing megaprojects that could permanently reshape Europe if you're interested. But let's get back to Rogfast. The tunnel will consist of 2 separate tubes, each with 2 traffic lanes, fully dedicated to road vehicles. Safety walkways will be installed every 500 meters, along with emergency cross passages allowing evacuation from one tube to the other in case of an incident. This extraordinary structure will include 17 technical buildings, 154 emergency stations, 38 cross galleries, and rescue access routes between the tubes. Each tube will measure just over 10 meters in diameter. Rogfast will also rely on a longitudinal ventilation system powered by jet fans, specifically designed for tunnel ventilation and smoke extraction in the event of a fire. Air inlets and outlets will be distributed along the entire route, including at the tunnel's midpoint. There, 2 vertical ventilation shafts are being excavated, approximately 230 meters deep, with diameters of 8.6 and 9.4 meters. These shafts, along with several ventilation tunnels, will extract polluted air from one shaft while supplying fresh air through the other. This is also where one of the project's most impressive engineering feats will be located: a double underground roundabout connecting to another tunnel leading to Kvitsøy. In this section, the maximum gradient will reach 7%, while elsewhere in the tunnel it will be limited to around 5%. In practical terms, that means descending 7 meters every 100 meters at the steepest point. At this precise location, the tunnel will lie 266 meters below sea level. And it goes even deeper, down to 392 meters, making it the deepest road tunnel in the world. For comparison, the Channel Tunnel between the UK and France is 50 kilometers long, with a 38-kilometer underwater section, but it only descends to about 75 meters below sea level. As of today, no road tunnel anywhere in the world goes deeper than 300 meters. So why go so deep? Just to break records? Not really. Unlike other large European projects, Rogfast is being blasted and drilled directly into solid rock, rather than assembled from prefabricated tunnel elements placed on the seabed. In other words, it's excavated beneath the fjord, not laid on it. A strict rule applies, maintaining at least 50 meters of rock between the tunnel and the water above. This method, widely used in Norway, ensures long-term stability under extreme water pressure. But this approach comes with major challenges. An estimated 8.5 million cubic meters of rock will need to be excavated. While construction will inevitably impact the environment, Norway, one of the world's largest oil exporters, aims to follow an ecological strategy. Most of the extracted rock will be reused for local projects, including the creation of industrial zones near tunnel entrances and exits. The largest disposal site will become a new industrial area on Kvitsøy. Another challenge? Precision. To save time on an already lengthy schedule, Rogfast is being excavated simultaneously from both ends. The goal is for the 2 teams to meet with an error margin of less than 5 centimeters. Any greater deviation would lead to major technical, financial, and scheduling complications. This is surgical engineering, requiring cutting-edge technology. On site, rotating mirror laser scanners measure newly excavated sections, collecting up to 2 million data points per second to create a digital twin of the tunnel. This model is then compared to design plans to detect even the smallest inaccuracies. It's a far cry from the romantic image of surveyor peering through an instrument, explains Burkhard Bokum, CTO at Hexagon, a Swedish industrial technology group. But it saves time, money, and avoids costly material errors. Engineers also rely on advanced grouting and waterproofing techniques to keep the tunnel dry and stable, constantly fighting the risk of seawater infiltration. Despite all precautions, significant saltwater leaks have already been detected at depths of 300 meters below sea level. One of the biggest challenges so far has been finding grouting methods effective enough to seal the rock. We are constantly working to identify the best methods to ensure safe and efficient working conditions for everyone, Ann-Britt Moen told CNN. This extraordinary project is already very real. Construction began in January 2018, but was halted in late 2019 due to cost overruns, leading to contract cancellations and a full project restructuring. The COVID crisis then paused work for several months. Construction resumed in late 2021. According to the current schedule, the first vehicles should be able to drive through Rogfast in the summer of 2033. Estimated cost, 25 billion Norwegian krone, or more than 2.1 billion euros. The remaining question is, who will pay, and at what cost? Norway is an extremely wealthy country thanks to its oil and gas revenues. The government has announced it will cover 40% of the project, with the remaining 60% paid by drivers. As is common in Norway, tolls will be installed to repay construction costs. Around 6,000 vehicles per day are expected at opening. But how much will it cost to use the tunnel? For now, no one knows. And what if tolls are high enough to discourage drivers? Again, few answers. At full operation, traffic could reach 13,000 vehicles per day. But if it exceeds expectations, congestion could emerge, potentially reducing the project's initial benefits. Critics also point to other weaknesses, accusing authorities of overlooking safety, environmental and budgetary concerns. Environmentally, opponents argue that dumping massive volumes of excavated material elsewhere in the fjord could harm ecosystems and biodiversity. In terms of safety, scenarios involving accidents, fires or blocked tunnel entrances are seen as blind spots. That said, large infrastructure projects always face opposition, sometimes justified, sometimes not. No road is safer than a two-lane tunnel with no oncoming traffic, responded Oddvar Kamo, project manager at Statens Vegvesen, Norway's road authority. As for the unthinkable, he adds, it can just as easily happen on a plane, a train, or a ferry. To address potential risks, a real-time alert system will detect breakdowns, traffic jams, and incidents. Cameras and radar systems will continuously monitor vehicles. Finally, critics also highlight potential regional economic impacts. If Rogfast succeeds, ferry services and the jobs linked to them could disappear altogether. And for good reason. Rogfast's ultimate goal within the E39 modernisation plan is to eliminate all ferry crossings by 2050. Authorities, however, emphasise future jobs tied to tunnel operations and maintenance, as well as potential economic growth from new industrial zones planned at both ends of the tunnel. For now, construction continues. In November 2025, Norway's public broadcaster NRK reported that the E03 section between Mekjavik and Kvitsøy had reached 52% completion. It's the largest and most complex of the project's 4 sections. A clear sign that work is progressing, even though many milestones remain before the plan's 2033 opening. At long last, it appears that one of the most geopolitically powerful tunnel projects in history may finally become a reality. For more than a century, leaders in both southern Europe and North Africa have been dreaming of some way to build a fixed link across the Strait of Gibraltar. A tantalizingly narrow strip of ocean, just 14 kilometers wide at its narrowest point, between the Atlantic and the Mediterranean, and between Europe and Africa. Over several generations' worth of effort, numerous obstacles have continued to prevent such a project. Everything from cost to politics to uniquely challenging geology. But in the 2020s, things have been changing. Diplomatic relations between Spain and Morocco have been improving. Morocco's high-speed rail ambitions have grown, and for the first time in the project's modern history, a leading TBM manufacturer has reportedly concluded that the long-sought fixed link between Europe and Africa is actually feasible with today's technology. What this means is an English Channel-esque tunnel running underneath the surface of the ocean between Spain and Morocco, which would redraw the mental map of the Mediterranean and likely transform Euro-African relations. However, it won't be cheap, and it won't be easy either. In fact, it will be the most politically consequential, most technically difficult, and potentially deepest undersea tunnel ever made. Join us in this episode of Looking For as we explore the exciting yet daunting Strait of Gibraltar Tunnel. Few projects we've covered on this channel have been envisioned for longer than this one. The first time a tunnel across the Strait of Gibraltar was formally considered, it was 1869, and that was a remarkable time to be thinking about a link to Africa. Spain had just overthrown Queen Isabella II and had begun writing a liberal constitution in an attempt to reinvent itself as a modern European state. It was the middle of the railway age, and the enterprising spirit of the era led engineers to wonder for the first time if such a project could actually work. Britain had built the world's first subaqueous tunnel under the River Thames roughly 2 decades earlier, and France was constantly constructing what would become the first great alpine tunnel at Mount Cenis. But most significantly, the very same year Spain first considered the Strait Tunnel, 1869, the Suez Canal was completed in Egypt. Then the flagship of intercontinental trade infrastructure in the emerging modern world. However, despite the optimism, a tunnel linking Europe and Africa was still wildly ahead of the technology. The next major moment of consideration came in the year 1930. A March 1930 issue of the magazine Popular Mechanics describes how Spanish engineers had sunk a, quote, preliminary shaft to determine rock formations. The article also explains that the tunnel would have to be 20 miles from end to end and more than 1,500 feet, or about 460 meters, below the surface of the water. This reveals that, by this time, scientists had already determined that simply bridging the smallest gap in the strait would not be feasible due to the extreme depth of that narrower section. Popular Mechanics even published an update in August of that same year with the intriguing title Strangest Tunnel to Join Europe and Africa, showing a drawing of a huge concrete tube that would house a full-gauge railway and a motorway for cars. But despite these promising developments, engineers again concluded the technology simply did not yet exist to make the vision a reality. It wasn't until 1979 that King Hassan II of Morocco and King Juan Carlos I of Spain signed a joint declaration to initiate official studies of a fixed link between the two countries. Roughly 2 years later, in 1981, Spain established SEQEGSGA, an acronym which, translated from Spanish, stands for Spanish Society for Studies on a Fixed Link Across the Strait of Gibraltar. And for almost half a century, alongside Moroccan counterpart SNED, the Strait of Gibraltar has been meticulously studied. That time frame might seem ludicrous, and yes, bureaucracy, money, and politics have all played a role, which we'll get into. But tunneling through the strait really is that difficult to study comprehensively. Even in the late 20th century, planners were still wrestling with basic questions, like what is actually under the seabed. Answering that alone meant investigating deep high-pressure water, strong currents, seismic risk, unstable geology, and more. And even when they found answers, the solutions kept depending on technology that either didn't exist yet or couldn't do the job safely. That being said, the last 45 years have witnessed significant progress when it comes to zeroing in on what will not work, and therefore, by process of elimination, what might. One key thing they established is that the shortest route is not the best route. The narrowest portion of the strait in fact turns out to be near its central abyss, which reaches a depth of roughly 900 meters. The best route, or more accurately, the least unsuitable route, was revealed instead to be through the Camarines Sill, a shallower submarine ridge to the west of the narrowest point. This makes the proposed tunnel much longer, perhaps by a factor of 2.5 or even 3, but it also makes it possible. Numerous other important details were uncovered. A bridge was seriously studied, but eventually pushed aside for a variety of reasons, including the strait's busy shipping traffic, the difficult tectonic and geological features, and the need for unprecedented distances between supports, as much as 5 kilometers. Also pushed aside was the idea of a tunnel for cars. Planners also learned a lot about the material they'd be tunneling through. Mostly flysch in post-flysch formations. These are thick, uneven layers of rock, sandstone, shale, marl, clay, and limestone that built up as the mountains and seabed in the area were slowly forming and shifting. And in the process, they discovered buried paleo-channels, essentially ancient underwater valleys that got filled in and hidden under the seabed, which present the additional risk of suddenly encountering soft, unstable material midway through the tunneling process. But despite the accumulating knowledge, the project essentially remained caught in a loop for decades. By the 1990s, the project was well beyond the stage of being a mere fantasy. But while there was plenty of funding for pre-feasibility and feasibility studies, there was never enough certainty to fund full construction, because that required answering key questions like how much it would really cost, how long it would take, and what odds there were of overruns or of disaster. It also didn't help that Spain and Morocco have had recurring tensions over Western Sahara, migration, Ceuta and Melilla, fishing, security, and broader regional politics. Suffice to say, it's complicated, and a tunnel project of this scale requires nothing less than extraordinary diplomatic stability. Throughout recent decades, the project has also suffered from a lack of urgency compared to more immediate crises. While the tunnel would be a massive upgrade, it doesn't necessarily solve any glaring emergencies. But perhaps most crucially, it was simply never clear that tunnel boring technology could safely excavate the deep-sea terrain. For most of the 20th century, long tunnels were often built with some mix of drill and blast, road headers, compressed air work, and early tunnel boring machines, or TBMs. The older machines and techniques were usually best when the ground was relatively predictable. If they hit mixed ground, hard rock 1 minute, clay the next, and so on, progress could become dangerous or even downright impossible. The machine could jam, the face could collapse, water could rush in, tools could quickly wear out, and the project might simply devolve into a money-burning, equipment-frying trip to nowhere. Modern TBMs, on the other hand, are markedly different. In fact, they're closer to sealed underground factories. They can excavate, support the tunnel face, remove spoil, install concrete lining segments, monitor ground behavior, and continuously adjust operating parameters. They are therefore way better at working through mixed ground. And this is the development that the straight tunnel needed. It wasn't a matter of simply building a bigger drill. Constructing the straight tunnel requires a different generation of machines, one that can dig while holding back the sea, read the ground as it moves, and build the tunnel behind itself, meter by meter. And this is why, in 2025, German TBM manufacturer Herrennecht reportedly produced a landmark study concluding, for the first time, that a twin-bore rail tunnel between Spain and Morocco can be excavated using current tunneling technology. The significance of this announcement would be challenging to overstate. Herrennecht is one of the world's leading TBM companies, and their unprecedented conclusion marks the end of what would be called a 1.5 century era. Since the late middle 19th century, leaders have been grasping at this seemingly unattainable dream. At long last, it's finally safe to say it's unattainable no more. But of course, that is a far cry from saying it will succeed, let alone when. Just because the tunnel is now possible does not guarantee it will be built. There are other obstacles for Spain and Morocco to still overcome. One is political commitment. Recent reporting says both countries may decide around 2027 whether to proceed with an initial exploratory tunnel, which is another way of saying it could be at least another year before Spain and Morocco formally decide whether to build the tunnel or not. Reports also state that it's believed the project would take at least a decade to complete and will cost an estimated 8.5 billion euros or $9.9 billion US dollars. Accounts vary, sometimes with alarmingly wide discrepancy, about some of the proposed tunnel's physical statistics. However, most seem to land somewhere around a 39-kilometer tunnel, nearly 28 kilometers of which would run underwater or beneath the seabed. Some reports mention a distance of 42 kilometers. However, this is likely in reference to the distance between terminals. The selected route through the Camarines Sill runs through a zone where the sea is roughly 280 to 300 meters deep. The tunnel itself will thus reach a maximum depth of roughly 475 meters below sea level. That's roughly the height of the highest roofline in the Western Hemisphere, Central Park Tower in New York City, and more than 6 times deeper below sea level than the Channel Tunnel between England and France. In terms of what will be inside the tunnel, we have some preliminary answers here too. The plan is for 2 independent single-track rail tunnels, each with an internal diameter of about 7.9 meters. There will also be a central service/safety gallery with a diameter of about 6 meters. These will be connected by cross passages every 340 meters or so. But as we mentioned earlier, the hardest obstacle is perhaps not the engineering, it's politics. Spain and Morocco have edged closer in recent years, but their relationship has deep fault lines, disputed sovereignty over Ceuta and Melilla, persistent friction over migration, and the long shadow of the Western Sahara question. A tunnel here wouldn't just carry trains, it would become a live border crossing between Europe and Africa. In other words, a physical checkpoint where customs, security, and immigration policy would have to work in lockstep every single day across 2 governments that have historically struggled to trust each other. Thanks in part to this assortment of obstacles, one thing we know for certain is that the tunnel will not be completed in time for the 2030 World Cup in Portugal, Morocco, and Spain, as originally hoped. In fact, assuming the 2027 exploratory tunnel goes well, the start date for construction is projected to be in 2030. And this means we're unlikely to see it actually open until 2040. By that time, the dream of linking Europe and Africa will be 170 years old. But no matter how long it takes, when the day comes, it will be far more than just a tunnel. It will be one of the most symbolically powerful pieces of architecture on Earth. The Mediterranean would not stop being a border, But it would also become something else, a bridge, and the ultimate poster child for a more connected Euro-African future.